Good morning, everyone. Happy Friday. Today we're going to be looking at lesson 30.2.3, which deals with an introduction to electric field strength. And this lesson, I believe, can be found on page 20 of your unit handout. What we're going to be doing in this lesson is learning about electric fields by comparing what we already know about gravitational fields to what we don't know about electric fields. So this is going to be done in the same kind of fashion that we learned about Coulomb's law. We compared electric forces and gravitational forces. Now we're going to compare electric and gravitational fields. We need to talk very briefly here about the difference between a scalar field and a vector field. The inverse square law, which we've been using with Coulomb's law for electric force and with Newton's law for gravitational force, the inverse square law is still true for electric fields. Then we're going to be looking at a couple of formulas for electric field strength, and we're going to be doing some calculations with those formulas. I want to go through a quick review here of some things that you, I hope, discussed in Physics 20. The concept of a field is a difficult one to wrap our brains around. The basic definition of a field is that a field is a three-dimensional region of space surrounding some source. And in order for you to determine that the field is there, you put in something called a test object. And the test object is affected by the field. It's influenced by the field. And I know this sounds very cryptic at this point in time, but I'm going to be using some examples to try to drive these key words home. The influence on the test object that you put in the field is evidence that the field actually exists. If I put a test object, whatever that is, at a point in space and nothing happens to it, it is not affected in any way at all, then that means that at that point in space, there are no fields present. So let's look at the following cases. There is such a thing as a heat field, and a heat field can be produced by the flame of a Bunsen burner. It can be produced by lots of different sources. But in this statement, when I say a heat field is produced by the flame of the Bunsen burner, I'm telling you that the flame is the source of the field. However, if I want evidence of the field being there, I need to put something in the field. And in this case, I'm putting a thermometer in the field, and it's going to register a temperature. So the thermometer is what we would call the test object. I have a heat field. What's the source of the field? A flame. How do I know it's there? I put a thermometer in there, the test object. And how is the test object influenced? It reads a temperature. Another example would be a light field. An incandescent bulb is an old school light bulb. They're very, very hard to find, but they are very useful in teaching physics. An incandescent bulb is not an LED bulb, it's not a halogen bulb, it's not fluorescent. What it has is glass, and in the glass there's a piece of wire which, when electrons flow through the wire, it glows. And that one end of the wire is connected to the side of the socket, and the other end is connected to the bottom. So when you apply 120 volts to it, that wire heats up and it glows. And that's what we call an incandescent bulb. I'm going into a little detail there because we will talk about these types of light sources a fair amount in Unit 3. Well, if I want a light field produced by an incandescent bulb, the bulb is the source of the field. If I want evidence of the field there, I have to put something in the field. And I'm saying we're going to put a light meter. There's actually this device, and if you've ever taken photography courses, or you've ever had photos taken of you by a professional, you'll notice that they have this little handheld device they hold in the room, and what it's reading is how much light is present. And there's a little needle on it, or there's a digital display. But the light meter is the test object, and it's measuring the brightness. It may register the brightness in something called candela, which is a unit of brightness. It may measure the brightness in something called watts per meter squared, but it doesn't matter. A light field, in this example, has a source that's the bulb, and if you want evidence of the field, you put in a test object, we're using a light meter, and you look at the influence, which is a digital display. A sound field can be produced in a lot of different ways. So I'm trying to get some work done on Sunday afternoon in my house. I'm working at my desk, and I can hear this thumping noise coming from the parking lot outside of my place. And that's because there's a car stereo playing some annoying rap song. Well, that car stereo is the source. And if I want to measure the actual level, I mean, I could do it subjectively by just using my ears, but I'm deaf in one ear anyway, so that's not really that useful. I can use what's called a sound meter. Many of you have heard of decibels. Decibels are measurements of loudness. The sound meter is the test object, and the number of decibels is the influence. It's the evidence of the sound field. And lastly, the one that you would have studied specifically in Physics 20, a gravitational field, and I'm using the Earth, the mass of the Earth as a source. By the way, just before I go on, I really want to highlight this to you. The gravitational field has a source that's the mass of the Earth. I don't want to just say it's the Earth. It's the mass of the Earth. Because in yesterday's lesson, I hope, yesterday's and the days before, I believe, I hope I made the point well enough that the thing that's responsible for gravity is mass, whereas the thing that's responsible for electricity is force. I just misspoke. I said correctly that the thing that's responsible for gravity is mass, and then I said the thing that's responsible for electricity, I said was force. That's not what I meant to say. The thing that's responsible for electricity is charge. So mass produces gravity, charge produces electricity. The mass of the Earth is the source of the field, and if I want to put any object in the field to test the existence of the gravitational field, the object that I put in, the test object, must have a mass. And what is the influence? Well, normally when I ask students this, they say, well, what is the influence? People say the mass accelerates, but it doesn't have to. Just, if you want, you can play along right now. Hold out your hand with a calculator in it. Is the calculator in the Earth's gravitational field? Yes. Is it accelerating? No. It's not accelerating, but it is experiencing a gravitational force. So some definitions now. Fields can be scalar fields or vector fields. A scalar field is simply a field in which the influence does not have a direction, and a vector field is a field where the influence does have a direction. In those four examples, the gravitational field would be a vector field because the influence is a gravitational force, and force has direction. However, the heat field would not have direction. It would be a scalar field because heat, specifically the temperature you measure, has no direction. Same with the light field. When you measure so many watts per square meter, it's not so many watts per square meter east. It has no direction. And the sound field, decibel levels or loudness of sound, again, is a scalar. So now I want to talk about field strength and forces. And the main gist of this little mini lesson is that, just to begin with here, fields and forces are different things. I mean, they're connected to each other, but they're certainly different. So the influence of every field that we study in this course is going to be a force. In other words, we will only be studying force fields, not heat fields or sound fields or any of that other stuff. And the types of fields we're going to study will be gravitational fields, electric fields, and magnetic fields. Field strength should be thought of as a comparison of the influence, which is the produced force, to the test object used. And I'm going to come back to that in a little bit, but it's a very important idea. So the field strength for an electric field is going to be something that compares the electric force to charge, because charge is what's responsible for electricity. The field strength for gravity is going to be something that compares the gravitational force to the mass experiencing it, because mass is responsible for gravity. So when we review gravitational fields in a minute and learn about electric fields, that will become even clearer. First of all, at this point, you just really need to know something. Field strength is not the same as force. They are connected to each other, don't get me wrong, but they are different things. Fields are not forces. What fields are things that produce forces. Fields explain forces. Forces exist because fields exist. So a gravitational field produces or is responsible for gravitational forces. A magnetic field produces magnetic forces. An electric field is responsible for or produces electric forces. So a warm-up here. In general, what two things determine the strength? In other words, the relative size of the influence of a field. We have to come up with two things here which determine the strength of any field. So you can't say the mass of the Earth or the mass of the planet. You can't say the size of the Bunsen burner flame. But what I'm going to tell you is, in all of these examples we've looked at, one of the things that determines the strength is the source. And we don't need to get into any more detail other than to say the source. So what I mean by that is, we can get a heat field produced in a number of ways. We can use a Bunsen burner, we can use a bonfire, we can use the sun. Those are all different sources. The other thing that determines the strength of the field is the location. More specifically, how close to the source you are, or how far away. The source is. And number two may seem like a very weird question, almost hinging on metaphysical or philosophical, but it's important for later. Does a field still exist even if you don't put a test object in the field? So when those people are playing that music in their car stereo, through their car stereo, if there's nobody in the whole neighborhood to hear it, is there still a sound field? Well, yes. The field is a thing that exists because if you put a test object in it, you see evidence for it. The test object itself is not part of the field. So we can just answer this by saying yes. And now what I would like to do is go through a comparison of gravitational fields and what you should already know about them, and electric fields which you do not know about. The first thing to notice is the symbol we use. These are both vectors. Gravitational field is given the letter G, it's lowercase. Someone has decided that the symbol for electric field is capital E. And it's important that whenever you write electric field, you put the vector symbol above it. Because of course, capital E can also stand for energy. And energy is not the same as electric field. If you want to write down just the magnitude of the electric field, then you do not just write this, because then you might confuse it for energy. You need to write that. So that's the first thing to note, is what the symbols are for electric fields and gravitational fields. What is a gravitational field? It's a region of gravitational influence surrounding a source mass. Now, whether your Physics 20 teacher explained it to you in those words or not, that's a fact. You need a source mass producing that gravitational field. Well, then an electric field must be a region of electrical influence surrounding a source charge. Again, not to put too fine a point on it, but gravity requires mass, whereas electricity requires charge. That's a pretty important connection between a property of matter and the resulting nature of the field or nature of the force. For a gravitational field, the influence is a gravitational force on a test mass that you put in the field. Well, the influence of an electric field is the electric force on a test charge. Now things take a turn here. They get a little bit more difficult. If I ask you what is the direction of the gravitational field, you simply ask yourself, well, which direction will the object that I put in the field be forced? So imagine me standing in front of you right now in the room, holding a calculator in the palm of my hand. I can feel that the gravitational force on that calculator is towards the floor. So that would mean that the direction of the gravitational field is towards the floor, because it will produce a gravitational force towards the floor. We have a problem here, though, because imagine that I had an electric field in this region of space, and there's no need to draw anything. Just imagine that in this region of space, I have an electric field. And I take a test charge, and I put it in this electric field. Well, when we put a test mass in a gravitational field, it experiences a gravitational force, and the force is towards the floor. But even if you knew enough information about this electric field, you can't tell me which way this test charge will be forced due to the electric nature. In other words, you can't tell me whether it's going to be forced to the left or the right. For example, if I told you that what we have over here that's producing the field, that's producing the electric field, is a negatively charged block of metal. That's the source of an electric field. It will definitely influence charges put near it. The problem here is I don't know whether this charge is going to be pulled this way or whether this charge is going to be pushed this way. So I can't tell the direction of the field. And I think many of you know the reason for this. It's that I don't know whether that charge that I put in the field is positive or negative. Well, it turns out that we all have the same rule to follow. The direction of an electric field is the direction of electric force on a positive test charge that's put in the field. That's the rule we have to follow, and you're going to get more and more used to this. So in my example here, if I say to you, what is the direction of the electric field in this region of space, what you do is you imagine putting a positive test charge there. There doesn't have to be anything there, but you're imagining a positive test charge there, in which case you can see it would be attracted to that negative block of metal, which would mean the electric force would be in that direction, which means the electric field would be in that direction. Gravitational field strength is defined as the ratio of the gravitational force to the amount of the test mass. This is what I was talking about earlier when I say a comparison of the influence to the property of matter. This is your formula on your formula sheet from Physics 20. And I'm not sure, but I think on your formula sheet they don't have vector symbols or they don't have absolute value signs, and I think they should. I don't want to get into a discussion in this video about it. I think those absolute value signs, though, are important. What does this mean? It means that when we say the gravitational field strength of the Earth is 9.81 newtons per kilogram towards the surface of the Earth, we're saying for every kilogram of matter you put in the Earth's gravitational field, it experiences an influence of 9.81 newtons towards the surface of the Earth. And I know that your Physics 20 teacher may not have stressed this as much as I would maybe do it if I taught Physics 20, but newtons per kilogram are an important set of units here. We can write meters per second squared, or we can write newtons per kilogram. Well, by comparison, electric field strength is defined as the ratio of electric force to the amount of test charge, which means we have that formula. You also are taught last year that gravitational field strength can also be found using that, where this is the source mass. Now, I want to talk about this a little bit with you. We have Fg equals g times the test mass that you put in a field times the source mass of the field over r squared. This is just Newton's law of gravitation relating the force to the test mass and the source. If I divide both sides of this by the mass of the test object, I get g times the mass of the source over r squared. But listen, this thing, if you just look up on your handout, it's equal to gravitational field strength. This is equal to g. And since that thing is also equal to this, g is also equal to it, which is what I'm telling you here. I'm not going to go through the derivation, but there's a similar kind of comparison you could make where you can find electric field strength by saying it's kq over r squared, where q is the source. When you look at your formula sheet, I just want to go through these quickly with you here. Here are your gravitational field formulas, and here are your electric field formulas. Again, I believe it's better to write this formula with absolute value signs. I think it's important. And the same with this other formula. Electric field strength has a magnitude that's equal to the magnitude of the force over the charge. And when I'm back in the class with you at an opportune time, I will explain to you the significance of that. But for the meantime, just get in the habit of writing them. All right, we can get into some examples now. You know, the biggest thing, I suppose, I wonder if I have this here that I can refer to. No. The biggest thing is this. When you're looking at this formula for electric field strength, and when you're looking at this formula for electric field strength, Q here is the test charge, and Q here is the source of the field. That's the most important thing to note. So what is the magnitude and direction of the electric field 4 centimeters away from this charge? Well, this would be the source of the field. So we're going to use this formula to find the magnitude of the electric field. We're going to take K, which I'm just going to write as K, times 2.5 times 10 to the negative 6 coulombs, divided by 0.04 squared. K is 8.99 times 10 to the 9 times 2.5 times 10 to the negative 6 divided by 0.04 squared. Double check my work. And we get this number, 1.4 times 10 to the 7. And Since electric field, if you look at the formula on the left, since electric field can be calculated, not in this question, but can be calculated sometimes using force divided by charge, the units of electric field are newtons per coulomb. And there's a way to go from here to newtons per coulomb, but again, I don't want to, in a video form, get sidetracked. I want you to be able to use the formulas today. So again, when the time is opportune and I'm back in class, I will explain why those are the proper units, regardless of the formula you use. Now, that's the magnitude. What do we put for the direction? Well, the source is a negative source. So you have some charge that's negative, and this is the source of the field. You were told about 10 minutes ago the direction of electric field is the direction of force on an imaginary positive test charge. So if I imagine putting in a positive test charge, it will experience a force towards that source. So for a direction, we can put toward the source. The positive test charge experiences a force towards the source because the source is negative and opposites attract. And that's number one. Number two, what's the acceleration of an alpha particle in an electric field of a particular strength? This alpha particle is being placed in an electric field, so this is what we would think of as a test object. Now, before we get to the solution, I'll go back because I have them here. When we take a look at this formula for gravitational field strength, where it's gravitational force over mass. In other words, when we look at this, I would be willing to bet that most of you think of the formula this way. In fact, it's interesting because there are always Physics 30 students who, when I point out to them that it's not written this way on their formula sheet, they're a little shocked. It's written this way. But that's how we typically find a gravitational force. To find a gravitational force on a mass, you take the mass times the gravitational field. To find an electric force on a charge, you take the charge times the electric field. And although this formula that I've written is just a variation of that which is on your formula sheet, I think that this one that I've written is more memorable and useful. In our example, number 2, the force on that alpha particle will be equal to Q times the electric field strength. And since you're asked to find the acceleration, what you're going to do is have to make use of F net equals ma, and let me rewrite that. The idea here is that when the alpha particle is in the electric field, the only force on it is the electric force, which means the electric force is the net force. And what that means is we can take QE and set it equal to MA to answer the question. Now, we have to go to our formula sheet to find a certain amount of information. For example, and I don't have a formula sheet handy here, I don't think, go to your formula sheet and look up the mass of an alpha particle while I pull up my formula sheet. You should be seeing the mass of an alpha particle as being 6.65 multiplied by 10 to the negative 27. If you look at my screen, it says alpha particle 6.65 times 10 to the negative 27. So that's the mass that we're going to throw in here. times the acceleration. I'm going to drop the pretense of vectors here. We don't really care about the direction in this question. I do have the electric field, which I'll write down in a second, but I need to put the charge in. Now, when you look at your data sheet, you can see the charge of an alpha particle. You can see the charge of an alpha particle is given as positive 2e. And if you glance your eyes over to the constant side, we talked about this a couple of times over the past couple of days. The elementary charge is lowercase e. So putting this all together, if I tell you that the charge of an alpha particle is positive 2e, and e is the elementary charge of 1.6 times 10 to the negative 19, then what that means is the charge on the alpha particle is 2 times 1.6 times 10 to the negative 19. And you can use your calculator for that if you like, but 2 times 1.6 is 3.2. We also have the 3.5 kilonewtons, which is 10 to the 3 newtons per coulomb for the electric field strength. And there's the equation that we've built, which we can solve for the acceleration. 3.2 multiplied by 10 to the negative 19 times the 3.5 times 10 to the 3 divided by 6.65 times 10 to the negative 27. Double check my numbers. 3.2 times 10 to the negative 19. Yep, we're good. Gives me an acceleration of 1.7 times 10 to the 11 meters per second squared. That's the answer for the magnitude of the acceleration. I don't know exactly how the question was worded, but we can't determine the direction because we don't have enough information. Number 3, if a proton experiences that force when put at a particular point in an electric field, then what strength of the electric field? Well, this is not the source. This proton is not the source. This is a test object, specifically a test charge. And electric field strength in terms of test charges can be calculated by taking the amount of the electric force over the amount of the test charge. This is why we've been writing newtons per coulomb for electric field strength. So all we have to do in this question is go 2.24 times 10 to the negative 15 newtons divided by the charge of a proton. If you go to your formula sheet and look up the charge of a proton, which I'm going to circle in green, this is the charge of a proton. It says positive 1e. Well, e is 1.6 times 10 to the negative 19. So all we have to do is divide those numbers. That's how many newtons per, this is how many coulombs. So about 14 kilonewtons per coulomb, or without being fancy with the metric prefixes, 1.4 times 10 to the 4 newtons per coulomb. I have one last question. You don't need to write this down. Let's just look up here together. What we're given is a diagram on the left-hand page, left-hand side of the page. You can see what I have. I have a metal plate that's positively charged and a metal plate that's negatively charged. And the idea here, everyone, is that this region is a region of space that contains an electric field. And we put an electron there. And it says, what is the direction of the electric force acting on the electron? Well, the answer to that is, since an electron is negative, the electron will be repelled from the negative plate. The electron will also be attracted to the positive plate. The electron is going to be forced from left to right. So the answer is going to be, for that part of the question, that the electric force acting on the electron is in that direction. The second part of the question says, what's the direction of the electric field in this region? Well, the answer to that is the electric field is in the opposite direction. Because when you determine the direction of electric field, you imagine a positive test charge. There is no positive test charge. It's something that you put in your brain and say, if I put it in the field, which way would it experience an influence? And it would experience an influence by being pushed to the left, which means that the correct answer is B. The corresponding assignment that goes with this is on page 23 of your unit handout, questions 1 to 10. As I believe I've told you, I hope and plan on being back on Monday. I've missed you all. I've missed being at work. And teaching this way is just not ideal. I can't see your faces. I can't tell if you're understanding things or not. And I apologize that it hasn't been perfect, but at least it's been better than nothing. So I hope to see you all on Monday. Try to get a list of problems for Monday from all of the lessons covered this week that you need help with. Or even just some general questions. Like, you're not quite sure how to rearrange Coulomb's law. I don't know. Many of you might have some general questions that are not specific to problems. I want you to kind of, as well as working on these for Monday, I want you to go through the week's lessons and find out what it is you need help with. And if we end up spending all of Monday's class just going through all of those questions that you have, that's fine. We don't have to move on Monday. So in the meantime, have a wonderful rest of the day and a fantastic weekend, and I really hope to see you all on Monday. Take care of yourselves.